Well, thanks for the invitation. I see there's lots of people traipsing in still, but maybe I'll give people a second just to be seated. So I'm going to talk today. My goal is to talk about, sort of how I can see, you all sort of making the biggest contributions to worldwide science, and that's really focused around the questions of kind of open, transparent, and reproducible science, which I see to be, a major thread in the development of science. I don't know how many of you were in the open science session earlier this afternoon. There we had a lot of talks about sort of the importance of these topics. Let's see. Okay, so I don't have to tell you this, right, that China's becoming a powerhouse in neuroimaging. This is just looking at PubMed citations for papers about fMRI, and China's overtaken Germany now. And given its trajectory here, we'll probably be catching up with the U.S. Fairly soon. So clearly, there's a lot of action going on, a lot of resources being invested in neuroscience in general and neuroimaging in particular. You saw Fudan has however many scanners, and so clearly there's a ton going on. My history is so many of you probably know Gui Zhu's at Beijing Normal University. Unfortunately, isn't here at the meeting. He was a postdoc in my lab back in the mid-2000s, and then moved to Beijing Normal. And so I've had a long relationship with him and with Qidong at Beijing Normal. And then Helen Zhao. Is Helen here? I haven't seen her at the meeting. Oh. So Jacques and I, she came to my lab and visited. So we've had a number of papers together. So we had this long collaboration. So it's been, really exciting for me to work with them and to continue to collaborate with them. I've also been impressed with all the work that's been done, around reproducibility, particularly, Jinyan has been sort of leading that charge and really pushing, for kind of the development of, in this case, data resources around, reproducibility and reliability. And we just edited together a special issue of Frontiers in Neuroscience on reproducibility and reliability in connectomics. And so I think, these are issues that are on the forefront of a lot of people's minds. But it's important to realize that these, doing this kind of better, open, reproducible science is not easy. And it's not easy anywhere. But it's particularly not easy in contexts where there's a lot of competition for jobs, right? There's really fundamental issues that need to be addressed, like the fact that when you do reproducible research projects, you're going to have fewer positive findings, right? So when I give talks and I say, oh, you should do all these various reproducible things, I try to make clear to people that, the things that I'm telling you to do are probably going to result in you having fewer papers. Your papers are going to be more likely to actually be correct, but you're going to have fewer papers because there's things when you're not using reproducible practices that can end up being a paper that when you're using reproducible practices, you will realize this isn't robust, I can't publish this. But the problem is that these incentives aren't aligned, right? When you go to apply for jobs, and this is the case, I assume this is the case in China, certainly the case in the US, that when people, you go to apply for faculty jobs, they're not looking at how reproducible are the methods that you're using, are you pre-registering all of your research. They're looking at how many papers you had in fancy journals, right? And I assume it's exactly the same, everywhere, right? And so the fact that, that I think it's changing slowly. Certainly for us, when we at Stanford look at job candidates now, we look at the degree to which they're using reproducible practices, and I think other places are coming around. But that's something that hasn't filtered out to most of the world yet. So I think it's important to keep in mind that what I'm trying to tell you to do is it's medicine that will taste a little bit bad going down your throat because ultimately it's going to. A colleague of mine has this idea of the career-wise false discovery rate, right? That you don't want to be the person who's always putting out papers that turn out to be false. You want to make sure that the papers you're putting out are true. And the things I'm going to tell you about are things that can help improve that career-wise false discovery rate. So I'm going to talk about two different things. One is pre-registration, and the other is the, reproducible analysis tools. So the idea behind pre-registration sort of came out of, early it came out of medical clinical trials, and then in the last 10 years it's become very popular in psychology because, psychology had a big crisis of confidence a number of years ago when it became realized that a lot of the work that was being done didn't really replicate. So the idea behind pre-registration is just to be very clear about what you're going to be doing in the study before you ever do the study. You write it down and you submit it somewhere where it's sort of safe, right? So people can, there's things like the Open Science Foundation, osf.io, there's other tools as well. The idea is just to write down what it is that you're going to be doing so that you can be sure later when you write the paper and you say, we hypothesized X or Y or Z, that you really hypothesize those things and you aren't making up hypotheses. It's very easy to justify things. You don't have to be trying to do bad things to sort of convince yourself that you expected something. One idea that we really like is actually, before you ever run the study, actually generate simulated data from what you expect, because then you can actually develop all of your analysis code on simulated data before you ever touch the real data, because it's nice to basically have all your analyses sort of as well specified as possible before you touch the data. For imaging studies, our analyses are really complex, right, and stuff always changes. But there's a few things that I think you should write down in a pre-registration. One is just what are the main questions you want to ask, your primary hypotheses. You're looking for activation in a particular region. You want to say, I'm looking for activation in a particular region, and also say how you're going to specify that region, if you're going to use a particular atlas or however that'll be specified. And then also talk about how you'll include or exclude people from the study. A group in Oregon has developed this template, this is the link here, that basically is an example of what a pre-registration for fMRI looks like. And so you can have a look at that if you're interested. And I wrote a blog post a while ago about pre-registration that sort of says a little bit more about this. Now, one misconception that people often have is, well, I don't want to pre-register because it limits what I can do. Then I have to do exactly what I wrote in the pre-registration. And that's not correct at all. What it really limits is what you can say in the paper, right? That you can pre-register and then you can do whatever you want, but the point is that you need to say in the paper, well, if we deviated from what we said we would do, then here's how we deviated. And it's never going to be the case that you're going to see a data set and do exactly what you thought you were going to do before you saw the data. This is an example of a paper that we just had that did this. This wasn't an fMRI paper, this was just behavioral work. Where we had started out with a pre-registered plan we put on Open Science Framework, but then when we started looking at the data, we realized that the plan we had didn't really work, and so we had to change what we did. We just said that in the paper. So we report what we did, and then we say we had done a pre-registration, and then we deviated from it in exactly these ways. The really important part is being transparent and clear about what you planned to do and then what you ultimately did. This has had really interesting effects in the medical world. So in the year 2000, one of the National Institutes of Health basically started requiring clinical trials to pre-register the outcomes that they were going to be looking for, right? So like if you want to give people a drug and you want to see does it reduce the number of strokes, then you have to write down it reduces the number of strokes. That's our hypothesis. Before that, what people could do is run a study, get a bunch of outcomes, and if any of them were significant, they say, hey, look, our drug works because out of these 10 things we tested, this one was significant. So the vertical line here with the flag, that's when that requirement started. And all of these things with pluses, these are all papers that claimed that their drug helped. They claimed a positive effect of their drug. Look at how many of those there were before pre-registration and then afterwards, right? Almost, you get a much higher degree of null results after pre-registration than you did before, and that's because these people were probably fooling themselves into thinking there was a positive result when really there wasn't. And so this gets back to the point about, pre-registration will help you probably find the truth better. It's also going to make your life harder because it's going to give you more null results. And obviously, we'd also like you to be able to, I think publishing null results is really important too, but fancy journals generally don't want to publish null results. I want to talk about another issue around reproducibility in imaging, which is analytic reproducibility, right? So that if you've analyzed fMRI data, there are almost an infinite number of different ways you can analyze the data, right? There's all sorts of things you can do, and we know that those choices can affect the results. This is one example. This is a paper published by Josh Karp back in 2012, where he took a single data set and analyzed it using almost 7,000 different analysis pipelines. And what it shows on the right is the range of z-statistic values that he got across those, from the highest to lowest, across those 7,000 analyses. And you see that there's, in some places, there's differences along the order of like 7 to 8 standard deviations, huge differences in the statistical values that just depend on the particular workflow that was used. And so this makes us worry about the degree to which, when we see different studies using different workflows, can we trust them? So one of the things that we've been trying to do is kind of develop relatively standardized workflows that people can use that we think are robust and that are well tested and sort of well implemented. So one of those is this thing called fMRI Prep, which is a tool. You can go to fMRIprep.org and you'll find it there. And it's all free and open source. And basically it does the entirety of fMRI preprocessing, from the raw data up through basically data that are ready to run statistics on, both in the volume and on the surface. And this is one of a number of what we call BIDS apps. How many of you have heard of BIDS? Oh, cool. So BIDS is this, for those of you who haven't, BIDS is a way of organizing imaging data. It basically tells you how you name your folders, how you name your files, how you organize your metadata. And once the data, if you have a data set that's in the BIDS format, a BIDS app can basically take that data set and do something with it. So if you want to run FreeSurfer on your data, right now you'd have to go, just using FreeSurfer off the shelf, you would have to go and like reorganize your data and then download FreeSurfer and run it. If your data are in BIDS, you can just take the FreeSurfer BIDS app and just point it at your data set, and it knows where everything is. You don't have to do anything special to run FreeSurfer, like reorganizing your data, because the BIDS app knows about it. And it's also reproducible because it's you know exactly which version, if you run it through this container thing called Docker, you know exactly which version you ran, so somebody else can come back and exactly reproduce the results, or you can come back and reproduce them later. And if you're a PI and you have students in your lab, you know how often it is that you want the student to reproduce what they've done, and that can often be very challenging for a complex workflow like this. So the BIDS apps help with that. Another thing that we try to do is, it's a really complex workflow, but we want to give people insight into what's going on and give them sort of good reporting to make sure that they can look at the data and make sure everything worked. So for example, you know that when you're registering a functional image to a structural image, that can sometimes go wrong, right? So we want to give people reports. The actual thing sort of zooms back and forth between the structural and functional image. You can't see that on here because it's a static version. But it also has the cortical surface outline on it. So it gives you these tools that help you kind of relatively easily look and see, did things actually work correctly, right? To do good quality control, which is also really important, because if you put, bad data into the analyses, you're going to get bad data out. We also give people, one problem that often happens is that people report the methods that they use in a way that you can't really reproduce what they did. You can't tell from the language in the paper exactly what was done. So we provide basically a script that you can put into your paper that tells exactly how everything was done, with all of the versions, like basically everything that the standards say that you should be using. This is just to show, this is how many people are running it or how many runs are happening per week. We basically, every time it gets run, it sort of calls home and says, hey, somebody ran it, it crashed or not. It doesn't send back any kind of real identifiable data, and you can opt out if you don't want it to report, but the default is for it to report. And so we're getting like thousands of runs per week in general. So a lot of people are using it and seem to be pretty happy with it. Joe Etzel from WashU has done some comparisons between the results, the statistical results you get when you use fMRI Prep versus the Human Connectome Project pipelines. And obviously this is dependent on this particular data set, but she found that fMRI Prep actually performed significantly better in terms of the statistical results than using the HCP pipelines to do the pre-processing. So we were happy to see this sort of independent validation of fMRI Prep. We weren't involved in this at all. So one thing I think we also have to think about is, I don't know if I coined this term, but it's a term that I think is important to keep in mind, called bug hacking, right? That when you're doing complex stuff, there's almost always going to be bugs, right? Very few of us are trained as software engineers, but we're still writing software. There's going to be bugs, and if a bug gives you a result that you don't like, then you're more likely to dig into that bug than if the bug gives you a result that looks good, right? So that's what this cartoon sort of says. Did it confirm our hypothesis? Yes, then stop checking it. And so I think that one idea that I've been pushing is basically to always assume that if something looks good, that you probably got it wrong. The principle of assumed error, right? And part of this is just like testing things, right? So generate simulated data where you know what the right answer is and make sure that your code can find the right answer. Or generate, take data and randomize them and make sure that the answer comes out the way that it should for random data, which is sort of similar to what Eklund et al. Did in their PNAS paper. So just to conclude, obviously, you guys have great potential. That the incentives for you and the rest of the world are still misaligned with reproducible research. And I hope that, many of you who are really engaged in the international community can lead by example by, going back and really showing that this is the way that science, in 20 years, these open and transparent and reproducible practices are the way it's going to be done. I didn't show it, but the National Academy of Science in the US just put out a report called Open by Design, which basically says, look, this is the way that science needs to be done in the future. So I think this is what it's going to look like, and if you want to be out in front of that, now is the time to start doing it. So thank you.